aldehyde, very strong electron withdrawing groups here, and the rate is 1. And we put electron donating groups in here, and the rate is 160. So we make the aldehyde, quote, less reactive. And in this system, it reacts 160 times as fast as the aldehyde. So isn't this interesting? So what's going on here? Well, we said, let's do a combination experiment. Because these reactions are so fast, people often measure the relative reactivities by copying the two electrophiles and comparing them. And if you do that, it comes out what you might call the right way. Okay? When you compare the two of them, now the electron-rich aldehyde is 1/30th as reactive as the electron-poor aldehyde. So something interesting going on, right? It's kind of stuff that's hard to walk away from. We figured this out. Okay, so here's what's happening. If you have both, let's just look at the system where you have both aldehydes present. The way this reaction works is that the aldehyde coordinates the lithium with a triple ion and causes it to dissociate. So this is a nucleophile-assisted cleavage. You can think of it as an SN2 reaction of lithium if you want. We get this species. Now this species could flip around and react, but it doesn't. It apparently dissociates to give the triple ion. Okay. Now, the electron-rich aldehydes are very good at doing this, right? They're the more basic oxygen, so they are good at dissociating the system. But they make the reactive species, but now it's the electron-poor aldehyde that captures the species. So the electron-poor aldehyde is more reactive in this test. But if you don't have, you just have one aldehyde present, the good aldehyde pops it open and then reacts, and seems to be more reactive in the system. Okay? I don't want to belabor the point, but and we were able to do all sorts of experiments and nail this thing. We really know what's going on in this particular system. So here's some things we learned. I can't show you so many in our spectrum. What is the relative rate of reaction between the electron-rich aldehyde, electron-poor aldehyde, when we simply allow it to react with the separated ion here? Okay. We measure a rate that's greater than 10 to the 9 for these systems. So there is, in fact, a huge inherent reactivity in these systems, which is sort of masked by these secondary effects that are going on and bearing all this. What is lithium catalysis worth here? So we can run the separated ion with HMPA present, in which the lithium is basically dead. It can no longer function as a Lewis acid. Or we can do it in THF, where the lithium is, as we've shown, is coordinated to the oxygen. And we find, again, about a factor of 10 to the 9 between these two species. So lithium catalysis on aldehyde is a huge effect that causes these different reactivities. Okay, one more small topic. I'll be done in 5 minutes. Okay. So enolates. Enolates are arguably perhaps the most commonly used lithium species. And as I've shown you a couple of times before already, enolates and THF, unhindered enolates, are usually present as tetramers. And for example, acetylphenol enolate or acetone enolate, nobody has ever seen anything but a tetramer. It doesn't matter what you throw in there. You can throw in polyligands, you can throw in HMPA. It's always a tetramer. Okay, these things are very, very sturdy tetramers. But we thought, our apparatus, maybe we can make a dimer, hitherto never before seen, by deprotonating it with a dimeric base. Okay? And so this is very easy to do because lithium diisopropylamide, LDA, as Dave Collin has very, very well shown at Cornell University, is a dimer. And we thought, well, if a dimer deprotonates a ketone, maybe what it's going to form is first a mixed dimer, and then it's going to form a dimer. And if we're lucky, we can see these species. Sure enough, if we do this reaction at, what's the temperature? Can you read that? -120? If you do this experiment, that's exactly what you see. The first species we see is not very well characterized, but we think it's the mixed dimer. In other words, this species here. And that goes away, and then we have a dimer. This dimer sits around, for hundreds of seconds. And then it slowly dimerizes again to form the tetramer. So this gives us an opportunity to look at dimer reactivity of a species that otherwise doesn't form at all. You can't get your hands on it. Let me just point out that at any point here, if you let the reaction simply go, everything is tetramer. So this species, if you stop here, it's simply warp this thing out, it will be tetramer. In other words, tetramer is the stable species under all these conditions. So we thought, well, maybe one can go one step further and actually make a monomer accumulate this way by deprotonating it with an amide that is monomeric. And again, Dave Colum, I called Dave up and I said, Dave, tell me a monomeric amide base, and he said, this one. So if you take this tetramethylpipridine and add this TN-10 reagent to it, you get a monomeric amide. And we injected acetophenol, perfluoroacetophenol, into this monomeric amide. And sure enough, after 2 seconds, what we see is a new peak, which we have characterized as a monomer. So this is a first monomeric amide anybody's ever seen. It does something interesting. If you watch it, you can see the time scale here. If you watch it, you get something that we eventually identified as a dimer, but you get an intermediate structure, which is this 2-to-1 ratio of peaks. And we played with it for quite a while before we had a clear picture of what was going on there. This species, it turns out, is a mixed trimer. It is a dimer which has sort of attached to one of the monomeric enolites. Okay, and it turns out this is what is called a parasitic equilibrium. We thought, isn't it curious that the mechanism of going from monomer to dimer involves a trimer as an intermediate? It is not just ridiculous, it's probably stupid, right? And we've worked that hypothesis for a while. But it turns out this is a parasitic equilibrium. In other words, as soon as you start getting some dimer formed, and you still have monomer present, the monomer and dimer combine to form this mixed trimer species, which has this structure. The lithium NMR has 3 different peaks, it's a 1-to-1 ratio. The fluorine NMR has a 1-to-2 ratio of different peaks. You see these two have one chemical shift, and this one has a different chemical shift. So this is a pretty well characterized species, and it simply goes back and forth, and slowly the whole system goes to the cubic tetramer. We have, of course, looked at the reactivity of all these things, and unfortunately, the range is not very good because these enolates are really, really reactive. Almost everything we throw in there for the monomer is like done in 1 second. So we would have had to go to some fairly unusual substrates to get rates of reaction that are measurable, even with our rapid apparatus. But here's just a little bit of information for aldehyde and ketone reactions. It turns out the different aggregates aren't all that different in reactivity. We could measure dimer versus tetramer quite well. It's one factor of 17. This is by far the smallest number that we've ever seen here. Turns out, aldehydes don't care so much about this aggregation effect. If you do the same thing with trimethyl iodide, which we have used in this case, we get big numbers. So the dimer is 85,000 times as reactive as the tetramer, which is a more typical number that we see. There's also some interesting effects on the O-to-C-silation ratio, so we now know something about the different aggregates have quite different ratios of reaction of oxygen versus carbon, which is one of the things that people have manipulated by this sort of effect. I'm trying to finish here. Okay, that's it. Okay, so that's my story. Usually in this kind of talk, what people do is they either go through everything they did in their whole life and get one slide on each and have a student's name on each, or you can take the latest project and go through it. I try to give you sort of a mix of both, so hopefully it wasn't too cursory. These are my last 4 PhD students who did a lot of the work that I talked about, and postdoc who's not on the screen. We used to play croquet in my backyard when we had our summer picnics, so that's a shock from my blood. And of course, I should thank these students and all the others. Their names have been on the slide. There's too many to list here. Special thanks to the chemistry department who hosted me for all this work and provided superb equipment for the wonderful co-workers to do all these many experiments. Believe me, it's a lot more fun to go through the results than to do work apart the rapid injecting experiment, which may have taken 6,000 NMR spectra in a period of a couple of hours, and then go through all these things and not look at it, figure out what it means, and so on. And then go to your professor and he says, oh, that's neat. Now we have to do this otherwise. Anyway, thank you. I can make you a copy. This thing was still being modified last minute, so I think there's a set view. But after that, makes sense.
Oh, question back there. Yeah.
From all of your NMR experiments, were you able to determine any of the separation between the entropic and anthropic components, I mean, the dissociations of these various lithium aggregates?
We did in some cases. They're usually mostly entropic. You can see from the slopes of these delta G plots, if the delta G plot is flat, entropy is 0. If it's slanted, it means a big entropy. And most of them were just slightly slanted, so that kind of, I think the numbers were there, but the entropy effects are usually modest. In other words, they're not as large as the entropic effects at any given temperature. I'm not one that likes to analyze entropy. I don't really understand it. And people who do always leave me with a little bit of queasy feeling, But I'm more into product ratio and rate ratios and stuff that's being real numbers.
I have a question. At the end of your career, looking back on it, what are the big questions that you wish you would have answered that you didn't figure out?
I don't know if there's big questions. There's a lot of little questions and a lot of little experiments one thing that we sort of took a half a shot at and never really went after is when you do reactions with lithium reagents with carbonyl compounds, you get oxide mixed intermediates. And the rates are such that we were in a position where we could have studied this effect very, very nicely because the barriers to interconversion are such that we would get good numbers. And so I always sort of regretted not going after that. That would have been a big project. But for example, when lithium adds to an aldehyde, you end up getting first, and we've seen some of this, a mixed tetramer which has one oxygen and 3 lithiums in the next one. And we could have measured the rates of all these individual species and sort of got to the bottom of all of these funny rate effects that people see all the time. Anyway, that's just a micro thing. I mean, it's a 5-year project, but on the big scale, but I don't know that I had any big plans that I couldn't do. I think I wound myself down at the end and sort of said, okay, I'm not going to be able to do this. Yeah, just the question.
Ian, you have any perspectives from organolithium chemistry in pharma? Sorry to put you on the spot.
Put me on the spot. I was thinking about something completely different.
As were many people throughout the talk.
So one thing that's troubled me a lot is like an addition reactions, because everyone used to run batch-based chemistry, used to miss all these effects. And I was just trying to connect in my mind rapid injection NMR as a way of probing what your resonance time would be in a flow reactor. That's what my mind was actually. Because a lot of the chemistry that we think that people have done, I think is incorrect, because often you run batch reactions cold and then you dump them into another component. I think of a manic reaction in particular. And the reaction will be scaled up when we actually realize that if we build a flow system and we use a 3D printed reactor, we have to get a resonance time of 200 milliseconds in the reactor. And that allowed us to take the reaction that was running batch on like 70, to actually run it at 0 and actually get exactly the same stereoselectivity. So it wasn't the stereoselectivity. You got a much higher yield because you didn't have all these other reactions going on. So I was trying to connect where you were with rapid injected NMR, how you'd actually connect that then to chemists practically running the reactions, correct?
Well, I think very directly. I mean, the experiment that you're talking about can actually be modeled exactly in these kinds of conditions. It's not really difficult to do this, but you do have to look at front-end method and the building apparatus of some sort.
And then the other question is practical. I've spent most of my career at the other end of scale of this. How do you make sure that you get all these new lithium in this syringe, which is now about a meter above where your NMR tube is, and you've got this cathode tube behind that? How do you make sure that everything doesn't just hydrate by the time it actually gets to the NMR tube?
Well, even more to the point, the NMR tube is open to all this. I mean, I'm going into the stir, I'm going to get into the food stuff, it's open, the NMR tube. The reason this works is because the cooling gas is nitrogen, it's pure nitrogen. So there is, in fact, a high-quality nitrogen atmosphere inside the tube. And we, in fact, developed specific protocols for boring the tube and for lowering the devices in there, because if we did that carelessly, we would spill some oxygen down into the tube and it would destroy our pure lithium. So, but in steady state, there's no problem at all with that. Now, you touched on another problem, which is, okay, you've got this NMR tube at minus 135, and the stuff that you're injecting is at the top of it is at room temperature, and as you go down the tube, it gets colder and colder, and the last little bit is minus 100 or something. How do we handle that? Well, it's pretty straightforward. We have a way of measuring the temperature inside the tube live on a second time scale. And so we have done experiments. I can show you the spectra, they're quite pretty. But when you inject in one of these solutions, say a 10th mil injection into a 2 mil tube, it's a big tube we're using here, the temperature jumps by about 3 degrees, and then comes back down again over a period of about a minute. Okay, so you're into kinetics. This is not ideal, right? Because down at these low temperatures, the degrees are fat, right? 1 degree means twice as much at minus 130 as it does in the temperature. So these are big changes. So we developed a protocol that was quite straightforward, and that is at the same time that you inject, you also raise the temperature of the spectrometer by the known amount of warming. And then the temperature jumps 3 degrees and stays, and it's almost perfect temperature control. So in the time scale of a second, everything is actually pretty good. But those are perturbations. This is part of the art of doing this experiment. I mean, for most things it doesn't matter, but if you do actual kinetics, you don't want the first quarter of the reaction to be 3 degrees higher than the last half. Okay.
Just a quick follow-up. Did you have any experiences based on these insights where pharma or other kind of industrial researchers had issues with selectivity, for example, in addition reaction or otherwise, where these kinds of activation states? I think Dave Collins always talked about
Dave Collins has been very successful at applying his insights to pharmacy and that connection. I haven't had that connection in my work. What I have noticed, however, is many papers where people do a reaction with some lithium reagent, do lithium or something, at minus 78, they put everything together, they stir it for half an hour, they warm it to 0 degrees, and then they quench it. And I know that their reaction was done in about 3 milliseconds, okay? So all the rest of this time simply allowed oxygen to get into the system, allowed things to decompose, and so on. It was wasted time. So a little bit of knowledge about how fast the reaction, it's worthwhile checking when you do these experiments so that you don't do this unnecessary, let's say, paralysis of your reaction mixture when the reaction is long. Now there are, of course, many reactions that are slow and then you have to wait for a period of time. But any addition to a carbonyl group is over. Remember, the rate limiting step for butyl lithium added to any carbonyl group is dissociation of the tetramer. Okay, that's the rate limiting step for all of these reactions. So they're all the same rate, basically. But yeah, no, I think the pharmacy people don't often get into this level of investigation. They tend to be sort of more careful in the way they solve these things. I think you probably agree that we
I think the work with college pretty well in terms of lithium tetramer and the separate cells. I think that for a post hoc characterization of the system, what was developed and what was before, what we really need is this level of understanding before we design it. I was trying to think, why did there was East Coast out there? Why did we ask Dave now to not come here? Because actually it would be more appropriate. In that case, you're adding an insight to put us out and you need more like yours rather than Dave's lithium hands. Job.
Yeah, Wisconsin's the place to be.
It's more difficult. Well, it's not. It's more difficult to get Cornell from you.
Yes, that's true.
It's more difficult to get to Cornell than to go anywhere else in the world.